Okay, I think we're going to kick things off. Thank you everyone for joining us for the second edition of Encrypt. We have a really great lineup, amazing speakers, and I think very interesting topics. In Encrypt, we're trying to create a niche for very kind of high quality, high level cryptography research that are focused on practical applications of cryptography. I think there are not a lot of those conferences, especially for blockchain, and we're very happy to have the second one. And thank you everyone for joining us today. So for the first speaker, I would like to introduce a man who needs no introduction, Nigel Smart. He is speaking here today on behalf of Zama, although he has many other affiliations, and he's going to speak about FHE, advanced FHE applications on blockchain. Yeah, without further ado, thank you, Nigel.
Yay, okay, here we go. So, welcome. As to kick this off, I'm going to be a bit of a rush because I've got to be somewhere else at 12 o'clock in town, so I might have to rush off at the end. I do apologise if you've got gazillions of questions. So, okay. So what I'm going to talk about is FHE for the blockchain. So this is kind of the blockchain as we currently have it. It's got high integrity, high availability, but zip confidentiality. Okay, so this is what we want to do is change this. So the integrity comes because it's distributed, and you have like the consensus mechanisms. The availability comes because actually it's distributed. Therefore, if one server goes down, it doesn't stop everybody accessing stuff. So, but it has zero confidentiality. Now, zero knowledge is kind of meant to be the privacy technology, and zero knowledge is cool, right? It's really, really cool. But often, zero knowledge is not actually used for integrity on the blockchain. It's used for what's actually verifiable computation. And in any case, even if you have a zero knowledge proof being used, the prover knows the secrets, okay? So in some sense, someone knows the secrets, okay? So zero knowledge proofs is good for some aspects of confidentiality, but it doesn't solve everything, okay? So what we would like to do is we'd like to dial up everything to maximum, yeah? Real spinal tap, put everything up at 11, and then we can, audience is a bit too young, okay, fair enough. Hey, some of you are of an age, great, okay. So it's important your age in this talk and your love of rock music, okay? It's going to be important, right? So we dial everything up to 11, okay. So that's what we want, but we might not be able to achieve that. So we have this thing called homomorphic encryption, and I hate this analogy of the gloves in the box, but let's kind of use that. So the idea is you just encrypt some shit. You can kind of encrypt it, send it somewhere, and then anybody else can kind of manipulate it, do stuff, and you can compute any function over the encrypted data, but only the person who has the decryption key can obtain the output of the function. So that's what FHE is. And actually, FHE is a form of technology which allows you to do MPC. So what's MPC? MPC is multi-party computation. So this does exactly what it says on the tin, multiple parties to do computation. Okay, so that's what it does, multi-party computation. So this allows many people to compute a function on their inputs, and only the output of the function is revealed. So if I wanted to compute the average, I could compute the average of all your salaries, and all that will be revealed is the average. Okay, so the inputs, your individual salaries, are kept secret. We won't worry about that there's a tax on that at the moment, because that's, in the sense that I could compute I could compute all of your averages except you, and then compute all of your averages, and I would then reveal your thing, but let's not worry about that for the moment. That's a systems level issue, therefore cryptographers don't care, right? So that's kind of a systems level problem. Anything we can't cope with, we push up to the systems level. Okay, so that's what MPC is. Okay, now Craig Gentry had an idea in his 2009 thesis. It wasn't just the fact that you had fully homomorphic encryption to create that, but you could use fully homomorphic encryption to do MPC. He explains this in about a paragraph in his thesis, so you might have missed it. So let's imagine we have Alice, Bob, Charlie and Dave, my super group of 1970s icons, okay? Okay? This side of the audience never heard of them, right? Someone here is like, yeah, rock and roll, yeah? Okay, so we have our rock band who they want to do some computation and they're going to talk to the cloud. So what they do in Gentry's FHE is there's some sort of threshold key generation produced. There's a public key which is put on the cloud and all the parties get a secret key. So that's what we have. We have a threshold key generation protocol, which is like a threshold key generation protocol for ECDSA. It's just, this is itself an MPC protocol, but again, that's a systems level issue how we implement that, so we push that over to the side, okay. Okay, now what we do is each party encrypts some data. So Alice encrypts something, Bob encrypts something, Charlie and Dave encrypt something, and they send something to the cloud. The cloud computes the function, sends it back, and then the parties execute a threshold decryption protocol, a bit like the threshold signing protocol, but done for decryption, and they get the output. So this is a brilliant MPC protocol. It allows multiple parties to compute any function on their input, and it kind of uses the cloud as this thing that just computes stuff for them. Okay, it's brilliant. Why is it brilliant? The first thing, it has low round complexity. It's there and back. It's really, really cool. The communication complexity is function independent. Mostly MPC protocols, the communication complexity actually depends on the size of the function. So this is really, really cool. It only depends on the input-output size. So that's the really cool stuff. The negative stuff, its security is shit, right? I mean, it's only passively secure, so that's really, really bad. There are going to be many attacks on this, and I've explained some of the attacks in this talk. And our goal is to remove these attack vectors and map everything over to the blockchain, so we can just deploy it on the blockchain. Okay? So that's the kind of idea. Okay, so what we're going to have is we're going to have our users, we're going to have a set of validators. There's Van Halen, Van Morrison, and Van Zandt, I think, is my 1970s brains code. And then we have a bunch of helper nodes. You know, help, you need somebody, help, not just anybody, so we get the Fab4 to give us some help. Yeah, so okay, someone's actually getting there's rock references here, so there we go, so that's really cool. So we have these, and then we're going to have a blockchain in the middle, so we've got some kids blocks in the middle, okay? So this is what our protocol is going to look like. Okay, so what we're going to do, the helper nodes, the beetles, are going to execute some threshold key generation protocol. They're all going to get a key, give one to John, one to Paul, one to George, one to Ringo, and they're going to send a public key, and then everybody gets the public key. Great, so this is kind of nothing much different from Gentry's protocol here, except we've just got more people and we've got more stuff going on. Okay, now the parties, this is your users of the blockchain, say, are going to encrypt shit and send it to the blockchain, or send it to somewhere. The cloud, if you want, okay? Even if you kind of want to be a Web 2 thing, this just sends it to the cloud. Okay, then the cloud is now actually going to be three things. We're going to have our validators, or you can imagine three clouds if you want to be a Web 2. This is Azure, Google, AWS, or whatever, and they can compute the function for you, okay? So we have that. Now what we're going to do, we've got the helper nodes, we're going to do the threshold decryption, and we get the function back, okay? So if we kind of go through the protocol again, can I go backwards? Yeah, there we go. So backwards, I encrypt, I compute, I decrypt. It's kind of nice and simple, yeah? So there's nothing complicated here. But if we do it like this, if we have the helper nodes, if we have the validators, then all sorts of things become super cool, super interesting, and super secure, okay? So, we've got to have a bad guy. So we've got to have a devil. And so we have, if you're on a highway to hell, there's only one devil you can have. So we have Angus as our devil. And this was the original attack against Gentry's cloud protocol. So if you did this on the cloud with, say, AWS, which is a kind of like a common use case of FHE, there is an obvious attack. The cloud just computes whatever function it wants. Okay? It can compute whatever function it wants. That can get you to accept any output you want. It could even just return Alice's output as the function. So Bob learns Alice's output, Charlie learns Alice's output, they learns Alice's output, and not actually the function they wanted to compute. So the cloud can do whatever they want. So we have to stop the cloud doing anything. Just doing anything. We want it to do a specific thing. Now that looks like a verifiable computation. So verifiable computation, you go back to how zero knowledge is actually used on the blockchain, it actually says, I've actually done what I claim to have done. I've actually computed the correct thing. Now there are various ways of doing verifiable computation. One is to take zero knowledge proofs and remove the zero knowledge bit, just say I don't care about the zero knowledge bit, and actually just run the kind of proof, the snark, not the ZK snark bit, and actually verify what's going on. Now that's a way of doing verifiable computation. But as we know, actually doing zero knowledge proofs on huge circuits or snarks on huge circuits is really, really costly. So maybe that's not the way to go at the moment with the current technology. However, we just had multiple validators. And there's a trivial verifiable computation protocol, which is the following. I think this verifiable computation protocol is due to Gennaro, and it might also have Gentry on the, I can't remember. Muti's going to tell me who originally came up with this idea, I can't remember. But the verifiable computation is you just duplicate it. So we duplicate it, we have Angus infects Van Morrison, and so Van Morrison actually computes G, but Van Halen and Van Zandt, they both compute the function F. Now because the computing the function is a deterministic function, we could just take a majority output. So we have these multiple validators. If there's an honest majority, we just take the majority verdict, and that's the value of the function. We don't know what the encryption contains. We don't know what CTF actually contains, but we know that CTF produced by Van Halen is the same CTF as computed by Van Zandt. So that's kind of a good thing to have. Okay, so that's attack one. But we solve attack one. Go back. We solve attack one by just having replicated the people who do the computation, in this case the validators, if you want to kind of use blockchain language, and we've then got honest majority validators give us verifiable computation for free, for cheap, whatever. I should point out that these validators, they might be doing really, really complex FHE operations, but these are going to be, but currently FHE is kind of meant to be slow, but actually it's not very slow because we can run at about the speed of a blockchain anyway, because blockchain transactions per second are, let's face it, shit. And so actually, slightly shit is kind of okay because that's fine, but it doesn't matter because actually we've already got a number of companies who are taping out chips at the moment and actually producing cloud services where you can play with hardware. Actually, you can play, I think Optalysis is a company where you can actually sign up to their thing and you can actually play with accelerators on the Amazon cloud already to do FHE. There's Belfort, which is no one in the audience from Belfort. No, okay. They don't have a sign-up method yet, but they can also do experiments on the cloud. And there's other companies like Konami, etc., who are taping out already. What else is there? Niobium is also taken out. Yeah? Anyone else I've missed? That's it, isn't it? Intel. Yeah, we don't count Intel. Yeah, okay, I missed Intel. Okay, yeah, fine. Okay. So there's a number of companies taking out chips at the moment which will accelerate by a factor of 1,000 at least some of the computation. So the validators are an issue in terms of speed. Okay. So the other problem we have is that encryptors could be bad. Alice could actually attack Bob. Okay, so Alice could actually be Bob, and in fact, Bob and Van Morrison might actually be in cahoots. They might be together as a bad guy. So what would happen here is that if you have Alice's ciphertext, this could actually be copied over as input, as Bob's input. And this wouldn't be detectable because actually FHE is, you're allowed to re-randomize ciphertext. So you could re-randomize the ciphertext in it. So Bob could actually enter Alice's ciphertext as his own. Now that might seem like, well, what does he get out of this? But if this is a voting thing, and all you care about is the privacy of the vote, not about can you influence the election, if you care about privacy of the vote, this breaks Alice's privacy. Because if whoever wins the election is definitely going to, it's either a draw or it's the person who Alice voted for. Yeah, so you break the privacy by being able to copy votes over. And that's kind of like a simple example, but there are more complicated ones. So what we need to do is we need to protect against Bob stroke Angus being able to copy an input over, or in some sense tweak the input in some way which might break the privacy later on, independent of the application we're running. So we don't know whether this is used for an election, we don't know whether this is used for something else or whatever. We need to make it secure no matter what functions they want to compute. And it's actually easy. We know how to do that because, well, let's step back a step. Why do we actually need to do this? Well, because the MPC security model says actually we need independence of inputs. It must be that my input is independent from your input because that stops this kind of cut and paste attack. Now that's actually important because of the voting thing, but it's also really important in the security proof because this, in some sense, is that it's what in the security proof allows the simulator to work. So there's something here that's going on that's actually intrinsic in the security proof. And the main technical issue is, for most MPC protocol designs, is actually how we solve this thing. But there's a classical solution to this, which is slap a zero-knowledge proof on it. So we know how to do zero-knowledge proofs, so we just slap a zero-knowledge proof onto the encryption, and then what does the zero-knowledge proof tell us? It says that the person who encrypted, if the proof is valid, knows the input. They know the randomness, they know the message, they know everything, okay? So having a zero-knowledge proof as input is, on the inputs, is kind of key. So what we do is that instead of just Alice sending a ciphertext encrypted A, she sends a zero-knowledge proof of A, that A is validly formed, plus a signature over the whole shebang to say, this is the thing that I actually computed and it was me that computed it. Okay? So this is kind of how you do it, and you have to slap the zero-knowledge proof on. And the zero-knowledge proof is slightly complicated-ish, because some of you might have seen Elgamal encryption before, and that's kind of easy because basically anything is encryption of anything. You know, any valid ciphertext, any ciphertext you can see is an encryption of something. Whereas that's not true of what's called LWE ciphertext, because we actually have to prove. Oh, I haven't got a pointer. Have I got a pointer? No.
It's the green one. It's the green one.
Oh, maybe not. It does. Oh, yeah. Voila. The big button which has a pointer on it is the pointer. Right, okay. So here we go. So an LWE ciphertext looks like something random times the secret, plus something small plus the message. Okay? So this is actually a bit more complicated than Elgamal. And you know, so not everything is a valid encryption, but what is cool here is that all we have to prove is that this linear relation holds. And proving linear relation holds is just subset sum problems. So all we need is zero-knowledge proofs of subset sum problems. So these aren't really complicated ZK snarks. Well, they are in some sense ZK snarks, but they're not complicated ZK snarks. They're kind of really trivial ZK snarks because we're just proving a linear relation. So, you know, these kind of protocols are really, really simple. We don't have to prove any multiplications are correct like you would normally do in zero-knowledge. This is just really, really relatively trivial. Okay, the statement might be slightly big, but you know, in some sense, this is a relatively trivial type of zero-knowledge proof. And there's all sorts of different techniques one can use here. You know, from I think the fastest we've got at the moment is vector commitment-based proofs. We've got MPC, which are not post-quantum secure, but we've got MPC in the head-based proofs. There's Ligero-style proofs. There's all sorts of other types of proofs around, and they're all relatively straightforward to apply in this situation. Okay, so what we have to do is that we have to actually prove that we have this statement where E is relatively small. So we have to prove that E is small. And the reason why we need to prove that not only just you know E, but E is small, because if E is too big, you have what's called selective failure attacks and all sorts of other things. So we've got two types of proof you can have. There's one using MPC in the head, which is due to some people from crypto experts. And there's one based on vector commitments, which is due to Ben Lidaire, who works for Zama. And there's pays your money, takes your choice. Do you want fast prover, large proofs, or slow prover, small proofs? Kind of decide whichever one you want. Okay, so we have this. So we can protect against Bob being corrupted. We can protect against Van Morrison being corrupted. Now, what happens if John's corrupted? So maybe I should replace Angus here with Yoko. I'm not quite sure, but there we go. And then again, like, it's only certain people who understand even who Yoko Ono is. It's kind of, oh my God, I'm getting old. Anyway, so Yoko Ono's come along. She's pretending to be Angus Young. She's corrupted John Lennon, and the Beatles are all falling apart. Sort of, bit of a problem. So what do we have to do? So we've got to protect against that. Now, what's cool here is that actually, there should be the title of the slide wrong here. So actually, we can do threshold decryption, and we can protect against threshold decryption in various ways. Now, we have a paper we had at WAC last year, where we can do this really, really efficiently if the number of bad guys is bounded by n over 3. So if the number of bad guys is bounded by n over 3, in this case, there's only John, and then there's a super fast protocol to do threshold decryption. If you make the number of bad guys less than t is less than n over 2, then the protocol becomes much slower and much more unwieldy. There's all sorts of other problems that you'll have. So t is less than n over 3 is kind of the optimal and provably the best in terms of performance, etc., and problems on the network and synchronicity and all sorts of other stuff. Okay? Okay, so what that gives us, if we go back to our picture, is in some sense we've kept if we kind of deploy that on the blockchain, what we've got an integrity we've still dialed up to 11, so that's kind of cool. We've actually we've got confidentiality, we've pushed that up, but we've had to pull down availability. And why have we had to pull down availability? Because if we go back, if more than T, and then if we corrupted, say, for example, John and George, then actually the two of them together could stop the blockchain running. Okay? There's a denial of service attack. Okay? And that's the key. So we've dialed up confidentiality, but there is an attack if too many people corrupt the threshold decryption, which gives us a denial of service issue. Okay? So that's why the graphs look like that. And there's further reading. There's all sorts of stuff here. You can read, what am I pointing there? I should be pointing there. I'm reading here. I should point here, I think. Anyway, so there we go. This is on the zero knowledge proofs, the two firms. The actual whole protocol I described to you is actually an MPC protocol. And you can actually, we've got a proof of security for the whole MPC protocol based on standard assumptions, normal assumptions. I won't use the word standard, that actually has a technical meaning. So normal assumptions is kind of, in fact, actually you can kind of see the whole protocol as a special case as the offline phase of the speeds protocol, but then extended slightly. So it's roughly the same proof of security as the speeds protocol. Then we have, there's some people from Zama got a whole white paper. This is being launched with lots of blockchain companies at the moment. I'm not going to list them because I'll forget one and therefore I'll piss them off, so I'm not going to list the companies that are doing that. But there's loads of stuff going on around town over the next 3 days, which I'm having to head off to in a minute to another one. And then we have this threshold decryption stuff. So that's kind of happening, and so this is coming to a blockchain near you. In the next few weeks. I mean, there's testnets running at the moment, I think, or the testnets starting to run this month, and should go completely live end of the year. End of the year, also hardware comes on, so this will all be deployed, etc. And any questions? Because I decided to go fast, so you can ask questions. I'll go you first.
What can we think about the typical values of TNN in practice?
The
typical values for the threshold.
Okay, so that depends. So really does depend on the institution that wants to run this. So we've talked to some organisations where they go, n is 40, t is whatever 40 over 3 is, -1. Some have gone 4-1. Also, you can do key rotation. So you might have a bigger pool, and then you go, for this hour, we're going to select you guys to use it, and we kind of assume that only, so you've got like a pool of 40, and then we go, you 4 guys are going to run distributed decryption for this period. So they it depends on the organisation, changing TNN. Theoretically, can you put the slides back up?
Yeah.
Oh, they're gone? They're gone, actually, the follow-up question is why can't you make t equals n-1, right? So that's the follow-up question. And that's because you get this. And no one wants a blockchain for which there's a trivial denial of service attack. Yeah? Because that's completely pointless. Yeah, so the point is that you kind of have this is what you kind of get, this is what we kind of get, and then if you kind of dial t too high, you get this. And so there's a kind of trade-off that you have to do, and we kind of thought that TSN-3 gives us a really good trade-off in terms of availability, because it means that every protocol is robust, information theoretically, the protocol itself is information theoretically secure, although the underlying thing isn't, because it's based on FHE, but because it's based on information theoretic primitives, it runs super fast. So we can do super fast reconstruction on asynchronous networks and stuff like that. So there's all sorts of tricks that we can apply with TSN-3 that we can't do otherwise, which gives us super fast throughput. Imad?
Another question. If you take a step back, what would stop you from using classical secret sharing?
Oh, what do you mean? Like what Cyprian's going to talk about next?
Spoiler alert!
Spoiler alert! Spoiler alert! Okay, so the key difference is, it's not, so the point is with classical MPC, you have a amount of communication which is proportional to the circuit, okay? And that's kind of fine. So actually, just go back, right? So in normal MPC, you have lots of communication, and it turns out that you can do functions currently with today's tech quicker with MPC than you could with FHE. Except two things happen. Number one is you need more communication, okay? Now, I can tell you this, computers get faster. The speed of light doesn't, okay? So, asymptotically, we know, as time goes on, FHE will beat MPC. Okay, we just know that, that's gonna happen, yeah? So this, in terms of performance, this must happen. The other problem is that if you have an MPC-based solution, the simple architecture becomes slightly more complicated. Because what you do is, I want to post my stuff to a blockchain, say it's a blockchain, okay, example. Okay, this also works on a cloud environment or whatever. So I post my input to someone else who does the computation. So I have to post the secret shares. So I have to know who's doing the computation, know what their public keys are, post to those specific people. I now have to then they have to do their stuff, they have to somehow validate and send the result back to me to be able to recombine if I'm doing a secret sharing based MPC. And so that's a level of complication from a systems level, because when I encrypt, when I enter my data into the system, I have to know who's going to do the computation. In this one, back. Where's my picture? Here we go. Here, yeah. You know, Alice has no clue that it's Van Halen, Van Zandt, and Van Morrison. Yeah, it could be any other Van. I can remember one. There's only three on the right because I went Rockstar's Van into Google and only three came up. So yeah, if you've got one, great. But anyway, so it could be someone else, and you don't have to know who they are. So the point is from a systems level, MPC stuff looks kind of cool, but it's much harder to deploy. Even if you look at Web 2 applications of MPC, it's very hard for companies to deploy Web 2 privacy applications of MPC. There's large, the only one that's vaguely successful, and I type vaguely in quotes, is Cybernetica. And they've been doing it for years, and they're mainly doing it for government basis. It's really hard to do. Whereas this is kind of much more plug and play. Hey, you want to engage in the system? Here's the encryption. Just encrypt some stuff. You want to get some output? Here's this. You want to agree on. There's a little bit of jiggery-pokery here is that we have to agree on the function. But hey, that's what a smart contract is. A smart contract is basically a program that everyone agrees on. Yeah, that's all a smart contract is. It's a program. It just happens to be a program you've all agreed on. So part of the issue with MPC is how do you agree on your program? Well, we've already taken that out of the picture because that's actually provided for us anyway. So there's kind of yeah. So I'd say it's doable, and Cyprian will obviously tell you that it's really doable, and I'm talking bollocks. But I'm going to go, so I don't care what he says, right? So Mutu's also going to say it's possible. Yeah. Okay. What's Cyprian going to say?
Yeah, is Zama planning to change its yellow on white thing, or?
Yeah, I know, it's a bit shit, isn't it? I know, yeah. What's weird is it looks great here.
Not from here, though.
I know. No, here it looks lovely. It's a beautiful yellow here. There it's a bit like my cap, where they provided the wrong colour caps. You know, so we're sending the caps back, that's why but go down to the trade floor, everyone's got, we spotted 4 companies with Zama yellow. There we go. Yeah, me too.
You can also assume honest majority among those, right? You already mentioned that.
Honest majority on the validators, yeah. But yeah.
So the input providers alongside with the proof, they post the signature. What's the purpose of the signature?
Just to say it came from them, because otherwise you could just copy the proof over. Yeah.
If someone is watching your presentation and they're like, oh, that looks like really cool, I'm going to build in the evening, like it's using for my project in the evening.
Yeah. Go ahead and do so.
What are the main problems and constraints that they would need while trying to use what you're telling about?
There'd be none. Just go look at our software. We've got amazing APIs. You know, so for example, just if you have an ML application, which is written in PyTorch, we have the equivalent PyTorch. You just add FHE into it, and it just does it. So you can do machine learning. You can do all sorts of stuff. Just go download the toolkits and just have a play. The Rust for smart contracts is relatively easy. Or go to the coffee shop, which is that way about a kilometre and a half, and there'll be talks on how you do this or today. So I bet if you turn up to those talks, you'll be doing it by tomorrow.
Okay, so you said that this is actually ready to use made it here.
Yeah, this is ready to use. All the compilers are done. Everything is done. Right, I can take one more talk, then I have to go to a taxi. Yeah.
Zero knowledge proofs are for like statements over
Yeah.
how efficient they are.
How efficient? They're super fast. I mean, so the slow one is like 10 seconds. The slow one is 10 seconds. The fast one is super fast. Oh, well, like we said, it's either MPC in the head for the slow ones, for the fast ones which are small, or we use vector commitments for the slow ones which are short. So but slow is slow. Slow is not slow. Slow is super fast that in your browser you don't notice. So that's the key, yeah? The user, if you have crypto where the user notices, it's shit. That's my definition of shit crypto, right? The user notices. You don't notice when you do TLS, apart from that little padlock going green. That's it. Okay, who cares, right? Whereas you used to, original SSL, it took you a second I remember, at least, when they got SSL handshakes down to the RSA component on your browser to under a second, that's like a major thing. But then again, the internet was slow then, and you normally wait 5 seconds for a page to load. But that just shows my age. Anyway, I have to go, so thank you very much.